Let me put the announcement slide. This is for next week, when we have the presentations.
How long do you expect the presentations to take?
I would schedule 15 minutes each, but are 14. This is how much?
3 hours and 30 minutes.
Yeah, so probably into
1 o'clock maybe.
15 minutes with questions, right?
50 minutes with questions, yeah. So that's going to be the challenge. Pick something that is interesting. First of all, let me tell you up front, you can't go wrong. There is no wrong presentation. Whatever you show us is welcome, but we will have a competition. So I am going to prepare a website where you can vote. Everybody in class will be asked to participate and listen to all the presentations, and then vote for the quality of the presentations. And in the end, the winner will get a little prize. That's going to be the challenge. So that's your audience. I have 1 vote, but you need to target like 14 votes, and if you add Max, it's going to be 15. And if we add Remy, it's going to be 16 votes. This is your challenge. Show us something that is cool. Pick something that is exciting. If you read the papers, the theory papers can be very dry. Some of them are just more dry than they should be. Distill out of that what you think is an interesting message that excited you, and that is what you want to present. Yes, Grace, please come in. Okay, so that is my announcement for next week. I think some of you might want to discuss your presentations. You don't have to, but if you want to discuss, I'm going to be available next Tuesday in the afternoon. I reserved over 2 hours because I have no idea how many people actually want to come. I have this little request. If you plan to come, just indicate that in the spreadsheet, so I have an idea of how many people want to come. If too many want to come, then we can always continue this on Wednesday. I'm also asking you to write a short report. 2 pages, 1 page, if you can squeeze it in 1 page. Tell us a story in a different language, in the language of a short report, the story of your presentation. And it's also a great exercise to run LaTeX. Yeah, some of you are experts, much more than I am. Some of you might be new to LaTeX. LaTeX is a system, the environment to use for any scientific publications. So I do expect these reports before the presentations. You don't want to do this afterwards. Afterwards is gone. The price is gone, so there is nothing for you left there. So you need to focus before the presentation on what you want to say. And in terms of how should we do it? Do people use PowerPoint or Google Slides? You haven't thought about this. If you, sorry? HTML.
No.
PDF is the standard format, I guess.
PDF, okay. This is PDF. Then I think you should bring your own laptop. You can switch this quickly. I'm pretty sure we won't have technical difficulties. So you bring your own laptop and you are responsible for whatever you want to present. All right. And I kind of got the wrong room. I reserved the smaller room. So the bigger room is 116. So I just made this correction today. I hope we get 116, but nobody uses it next Thursday. So 116 is a bigger room, 146 is way too small for us. All right, so today we are going to finish our discussion of Datalog. Datalog is a school language. It's very simple. Let me actually show it here. So quick refresher. So Datalog is a set, consists of a set of rules. The rules are all monotones. Each rule is a conjunctive query. Together, all the rules, they define an immediate consequence operator that maps the IDBs to new states of the IDBs. And this immediate consequence operator is monotone. It has a least fixed point, which is the same as a minimal model. The semantics is beautiful. This is what makes Datalog so appealing. So simple, so basic. And everybody loves this today, much more so than over 40 years of its existence. The problem is we cannot use negation. We cannot use aggregates. We cannot use negation. A lot of research has been dedicated on how to extend Datalog to use negation. And I'm not even an expert on all that literature. It's really a lot of literature, very deep theory. But I'm going to distill for you the most interesting aspects of the extensions of Datalog with negation. So here is an example of a rule that uses negation, and that is technically not allowed in Datalog because in Datalog, all the rules need to be positive. By the way, what does this compute? What is C here? What is the relation C? In just one rule. What is the operation here? How do we call this in relational algebra? The difference, yeah? It's just a wake-up call, making sure you got your coffee. So this is A minus B. We want to compute A minus B, but we cannot do this in Datalog. So here are 3 examples of Datalog programs that we would like to write, for which we need an appropriate semantics. The simplest one is, so we saw the transitive closure before. Imagine you want to compute the transitive closure of the complement graph. So the way we compute this, we first compute the complement of the edge relation, which are all pairs of nodes that are not in the edge relation. And then we compute the transitive closure as before. Seems seems a very reasonable Datalog program. Why not have a semantics for this? It's actually called semi-positive, and yeah, it's allowed. Here is a slightly more interesting one. We want to compute the complement of the transitive closure. Okay, so not the complement, not the transitive closure of the complement, but the complement of the transitive closure. So the intuition here is that we compute the transitive closure, but later we want only the complement. We only want the nodes xy that are not in the transitive closure. Okay, here is one of the nicest programs in Datalog with negation. It implements a win-move game. It's a single rule, but here we interleave recursion with negation. And we will discuss this in a lot of detail, this little program. So these are the kind of examples that we would like to be able to support in Datalog with negation, and we need the appropriate semantics for this. Why is it hard? Why is it hard to simply add negation to Datalog? And this is a prototypical example. It actually gets a little bit simpler, but I wanted to keep it like a meaningful Datalog program. S is our EDB. It has a relation, and suppose it has a single value, 1. And the Datalog program computes 2 IDBs, A and B. And A contains those entries X, which are not in B, and B contains those entry X, which are not in A. Big problem, because we have one fixed point. If A contains just 1 and B is empty, this is a fixed point. It's a model, right? So not B is true, and therefore A of 1 is true, as it should. And not A of 1 is false, and therefore B is false, as it should. But symmetrically, we have a second model. And the consequence is there is no minimal model. The standard minimal model semantics or the standard least fixed point semantics, that doesn't help us here. Okay. Oh, by the way, there is a certain model which is not a least fixed point, but it's a prefix point. Namely, we can set both of them to true, both of them to 1, and then all the rules are satisfied because everything applies true. Usually, this example can be simplified to something that looks like this. Here we have Boolean variables A and B, and the rule says A is true if not B, B is true if not A, and it's the same conclusion, even simpler. There is no minimal model. Yeah, this shows the difficulties of combining recursion with negation. Yeah, is it clear?
Sorry, you said that if in the prefix point both rules are satisfied?
Sorry?
Did you say in the prefix point both rules are satisfied or they cannot be satisfied?
Both rules are satisfied. It's easier to check here. Suppose A and B are true. Then what is not B? It's false. And false implies true. It's okay.
Oh, I see. Okay.
So there is no minimal model. And yeah, there are many models, and there is no minimal. Okay, good. So the difficulty is that the immediate consequence operator is no longer monotone. We need a different approach. So these are the approaches that I want to discuss. The simplest one, which is very natural and is adopted by all the systems, is to use stratified data log. And it's an even simpler version, which is just a semi-naive, semi-positive data log. And then there are two very subtle extensions, which are motivated by logic, by first-order logic, namely well-founded semantics and stable model semantics. And there are two other extensions that are more motivated by the computation, by how we compute the fixed point. Inflationary data log and partial data log with inflationary fixed point and data log with partial fixed point. And I will briefly mention them at the end. A lot of research and a lot of the literature is based on these two extensions, well-founded semantics and stable model semantics. So let's start with the simplest one, semi-positive and stratified data log. Essentially, stratified data log is an important one. So the semi-positive data log says that you can have negation, but the negation can only be applied to the EDBs, only to the input relations. Okay, so the transitive closure of the complement graph qualifies as a semi-positive data log program because we only negate the input relation, the edge relation. So we still have a monotone immediate consequence operator because the immediate consequence operator only acts on the IDB on T, and T is not negated. So therefore, the immediate consequence operator is monotone in T. And therefore, it has a least fixed point, and life is good. We can simply accept semi-positive data log programs without any change to our semantics. Okay, stratified data log. So here is how it goes. A stratification of the IDBs is a mapping from the IDB predicates to numbers. And each such number is called the stratum of that IDB predicate R. Now, every IDB predicate gets a stratum, like 1, 2, 3, 4, and so on. And the program is called stratified if there exists such a stratification, such that for any rule and any positive atom in that rule, the stratum of what you're computing in the head is greater than or equal to the stratum of what you're computing on. And for any rule and the negative atom in that rule, the stratum of A of the head is strictly greater than the stratum of B. So it's a little bit dry, this definition, but it says something very simple. it says that you can define the semantics of the stratified data log by simply computing the least fixed point sequentially for each stratum. For stratum 1, stratum 2, stratum 3, and so on. And the idea is that at each stratum, you can view the previously defined IDBs as EDBs. They are already computed. So you freeze them, and each stratum is a semi-positive data log program. Okay, so the output is called the perfect model of the stratified data log program, not to be confused with the minimal model. This is not a minimal model, it's a perfect model. So let me show you an example. The complement of the transitive closure is a stratified data log program. The IDBT is in one stratum, and the answer is in the second stratum. So what this means is that we first compute the first stratum. So we compute the transitive closure, which is it's recursive. So this is okay because T occurs here positively. So the stratum of this needs to be less than or equal to the stratum of that. And that's okay. And once we finish computing the transitive closure, this is when we compute the answer. This is stratum 2. So now we don't care anymore about T. T is like an EDB. So it's simply the difference between the cross product of the set of vertices and the previously computed transitive closure. Very simple. Now, notice this is important, and it's easy to miss this point. What we just described here, T being the transitive closure and answer being its complement, is not the minimal model of the entire program. If you consider the ICO, which takes both T and answer, where there is nothing about answer, but it takes T and computes the new state of T and answer, this is not monotone. For the simple reason that if you give me a bigger T, then I get a smaller answer. And the perfect model is not the minimal model. So the perfect model, what we are computing here, consists of the transitive closure and its complement. Can you think of a different model which is incomparable to this one? Neither bigger nor smaller. We played this game with transitive closure. Can you find a bigger model for the transitive closure? Yeah, the Cartesian product, all the pairs. Now, if P is all the pairs, then what is the answer? It's empty. Yeah, so we increased the transitive closure and we decreased the answer. And these two are incomparable. Yeah, so this would be a second model. It's not no longer the perfect model. It's an ad hoc model, an artificial one. T is a cross product, and the answer is the empty set. We discussed this a little bit a few lectures ago. The cross product is not necessarily a model. You need to what is it? Oh, it is a model. Yeah, it's always a model. So I ignore the footnote. Even if this is false, even if Z has no outgoing edge, this condition is false, but this is still true. It's okay to be true. Yeah, so the cross product is always a model. Okay, so this is all we need to know about stratified data log. It's by far the most popular extension. As far as I know, data log systems, they happily support stratified data log. For example, Soufflé does support stratified data log. And the same applies to aggregation. If you want to do aggregation, you just partition your program into strata, and then you do the aggregation in the next stratum. I guess, Max.
Would we be bothered by the previous slide?
This one.
Like the fact that is, also a model? Like that feels to sort of defeat the purpose of.
Yep. It's true. So it seems that this observation suggests that the perfect model is ad hoc.
So I think this comes from my perspective as a, Datalog implementer, but not understander. If you take an operational perspective or even like provenance-based perspective, this is nonsensical. Right, like
You
this
mean
model, the tuples in this model are not, in this fuzzy word, justifiable.
you mean in this model?
Yes,
But these ones are justifiable.
correct.
Perfect.
What is, how do we make that formal? That seems formal. Like, can we use a provenance-based semantics or something that makes sure that the things that we get, were derived from things that we wrote in the program, because I think that's what everyone wants.
Yep. Welcome to CS 294. We discuss it in a few minutes. Yes.
Is like, I feel like the issue here is that we're like, it's hard to compare outputs across strata. But like, could you like look at the highest strata, for example, and say the least, has to be at least 6 point of the highest strata in some sense?
Yeah.
Okay.
Yeah, that's the issue. If you compare IDBs across different strata, then something bizarre happens. But inside each stratum, you have a least fixed point, and their life is good. But Max has a point. Globally, how do we justify that this is the right one, and this is? How do we justify this is a bad fixed point? Unless you really order your rules according to this stratification.
I have a question on Zoom.
Yes.
Is there a way of thinking about this as some kind of like structural restriction on the hypergraph that you kind of define that defines like the Datalog program in some way?
It is a structural restriction, but on the rules. In some sense, also on the hypergraph. If you think about this query here as being a hypergraph, it simply says that you can't use recursion in T. T must have been defined previously. Is that where you were heading?
Something like that. I was wondering if like the strictly greater than means you have to have like separate levels in the graph or something like that.
Yes.
Okay.
So what this means is that in this rule, A can be recursive, co-recursive with B. You can have mutual recursion between A and B as long as they are positive. Or here you could have A, and then of course A has the same stratum as itself. But once you have a negation, then this P must have been defined earlier in an earlier stratum.
Right. Okay. Thanks.
As a consequence, this little program that created the difficulty that we discussed, this is not stratified. You cannot write this. If you want to write this program for whatever reason, you cannot. You're not allowed to write this if your system only supports stratified Datalog. Good. So a simple extension, which is stratified Datalog, which is easy to understand and to accept. It's operational. Let's now discuss the principled extensions that people have discussed. And there are two, stable model semantics and stable model and well-founded models. Both of these are best explained through this beautiful little puzzle, I don't know how to call it, the so-called win-move game. Let's discuss a win-move game. Here is a win-move game. We have a graph, a finite graph, and there are two players, and there is a single pebble that they move along the graph. We start at a certain position. The starting position is going to be our focus, which positions are winning, which are losing. And the players are just take turns. Player one looks at the pebble and moves it along an edge. Then player two continues moving it along the edge, some edge, and so on. The player who cannot move because there are no more edges, that player loses. Okay? And the question is, if I look at a node X, the question is if player one, who's the first one to move, if player one has a winning strategy. Let's see an example. Here is a little graph. You can see the directions. It's like a tree. Suppose my X is D. this is the starting position. Player one needs to move. Is this winning for player one? This is not winning. So here player one loses and player one also loses on B. What about C? It's pretty clear, no? And C, player one wins. Player one just moves to D and they win. But what about A? Is it a winning position for player one? Of course, because player one will move to B. If player one moves to C, they're screwed. Yeah, because then player two can win. But player one moves to B and therefore they win. Very simple.
What are the rules of this? I'm kind of, what are the rules of moving the pebble?
You can move them anywhere along an edge, directed edge.
You can't move on to something that sort of your opponent has moved on to already.
You could, if you have a cycle. Here we don't have a cycle. But if you have a cycle, you can go back. There is no history. Yeah, you start as a node, player one moves, player two moves, and whoever cannot move loses.
But what I'm saying is, like, can player one move A to B as well? Like, can two pebbles occupy one?
No, there is a single pebble. Yeah, so there is a single pebble, that's what you move, and
There's only one pebble on the entire board at the same time.
yes, there is a single pebble on the entire board. And the question is, if I give you a big graph and a node X, and start the pebble from there, from node X, does player one win from that position?
How is this just not like, is there some path of even length from like current?
Well, this is what this little example tried to illustrate. You see, you have two paths here, and you need a little bit of reasoning to figure out that indeed player one has a winning strategy.
Oh, because one player might try to move on, if you have an even and an odd path, then your opponent would move the one with the odd path.
Yeah, the opponent also has a vote, as it were. The adversary also has a vote. When it's your turn, they will choose the best move for them. Pretty fun little game. How do we write a Datalog program that, given X, tells us if X is a winning pebble? And by winning, I mean for player one, the one that moves first. Because for player two, it's going to be the doer. So we only focus on winning strategy for player one. It turns out it's amazingly simple. Here it is. X is a moving, is a winning position for player one. If there exists an edge to some other node X, such that Y is not a winning position for the first player at Y, which is going to be the second player. Yes?
You need to say something about leaves.
No. If X has no edge, then W of X is automatically false, because this rule doesn't fire for that X. Yeah, once you start thinking about the minimal model, it gets confusing because this is no longer a monotone operator. So we need to study how we define the semantics for a Datalog with negation that can capture in an interesting way this little program.
Like my question is more like there's no restriction that WX cannot be in the set if there's no implication for it so far, right?
WX cannot be in the set.
So like if there's not an edge, so you mentioned that like if there's not an edge, WX is default.
Yes, right. Because as Max alluded to, every time we make something true, we only make it true because it's justified by something. So if there is no edge from X to anywhere, then there is no justification to make X true. That is only intuition, because we are going to get to formal semantics, and then this will be captured there. But that is the intuition.
Yeah.
Okay, let's play more games. What about this one? which ones are the winning strategy for player one? Obviously, C is not a good one, right? What about B? Is player one? Yep. What about A? Is player one winning from here? No. So that is the solution. What about this one? This is the subtlety. So and D is losing and C is winning. What about B? If you start from B, where do you move?
Okay.
You move to A. You don't want to move to C because then you lost. So you want to move to A. From A, what happens? The other player will
Cycles.
and then it cycles. So so here it is. So it's the winning position. It's the winning position, but the other ones they seem to be undefined. Yeah. Something to keep in mind when we look at the semantics. We need to face this. Okay. Okay. So a little discussion. The same. What did I have a discussion here? Let me. Yes, I know why. Okay, so there is logicians long before Datalog, and there's a time when computers were just being invented in the 60s. They looked at extensions of logic with least fixed point. And there is a notation for it, least fixed point of a formula that has to be monotone. So the language that they considered was first order logic extended with a new syntactic construct, which is the least fixed point of a necessarily monotone formula. They didn't want to mess up with non-monotone formulas. The formula has to be monotone. My point here is that the win-move game, although we use negation, you can also write it without negation in a least fixed point logic. And here it is. It says find the fixed point W with all the nodes X such that there exists an edge. Oops, this should be and. What am I doing here? This is wrong. This should be and that should be implication. I'm almost tempted to fix it. Why don't I do it? Nope. Whatever that was. Okay, so this requires aborting. Good. So now you will see me fixing the for all, because this has to be and. This we know, we all know this very well. The existential quantifier goes well with and the universal quantifier goes well with implication. As you see, it takes quite a while to LaTeX. Note. Yeah, here we go. So we want to say that exists a successor Y of that node X such that there is an edge. And moreover, for any move that the adversary can make from Y, the adversary will put me in a new winning position. Okay. Question. This is completely monotone. W occurs here monotone in a positive position. Can we express this in Datalog? The answer is no. But what prevents us? What is the construction here that we do not have in Datalog?
The negation on the left-hand side of the negation?
The negation, yeah, but you can argue with this in semi-positive Datalog, this piece of the negation. It is universal quantifier. Yeah, so if you go back to this rule here, here y is existentially quantified. But if you substitute this w with its own definition, then this negation will transform the existential quantifier into a universal quantifier, and the new w will be positive. This is what happens here. Yes, this is why we can express the winning positions of the win-move game using a least fixed point, but we need this universal quantifier.
Is universal quantification also not really monotone then? Because if I like add something new to my set, it might not be true.
It's not monotone in this argument.
Yeah.
But it is monotone in the consequence. So here they just examine how these occur, and this occurs positively, and that's why it's monotone. But here is the interesting story. So in 1985, Chandra and Harel, they looked at stratified data log, and they said this is all we need to capture this logic least fixed point. The win-move game was not known then, but they thought, you know, we do these negations, and that's all you need to capture the least fixed point. And for Kionkolaitis, a few years later, disproved this. He showed that you cannot express a win-move game in stratified data log. Very interesting. And the fact that this was a bug in the paper makes it so much spicier. So why can't we why can't we express win-move in stratified data log? The intuition is that if you think about a tree, at each level of the tree, you need one negation. And in stratified data log, the number of negations is fixed by how many strata you have. So what Forkion did in his paper, he showed that if you have k strata, then you just have, you know, consider two different graphs with trees which are one level deeper. One has a winning strategy, the other not, and the data log program cannot explain between them. That was the proof. So in order to support something like the win-move game, we do need something better than stratified data log. That's a message. A lot of preparation for my two extensions for stable semantics and well-founded semantics. Both of them require two simple definitions: the grounded program and something called the reduct. The grounded program is something very simple. A grounded atom is just, or it's also called a fact, it's an atom without variables. It only has constants. For example, EXY is a general atom, XY are two variables, but E of A and B is a grounded atom. This refers to the edge from A to B. A grounded rule, same thing. It's a rule where all the atoms are grounded. Here is a standard data log rule. Here is a grounded rule. And the grounding of a program consists of all possible groundings of its rules on a given input database. So if this is our data log program that we want to evaluate, we can evaluate it by first grounding its rule in all possible ways. And here are the possible groundings on this graph. And then we evaluate this data log program. It's bigger, but now each IDB, each W is either true or false. Yeah, is this grounding clear? Good. The second concept is a little bit more subtle. It's called the reduct, and it's super important for both semantics. Let P be the grounded program, and let J be a set of grounded atoms. Think about these. These are the grounded atoms that I'm guessing will be true, and all the others will be false. This is the intuition. But set aside the intuition, let's look at the formal definition. So for any such set of grounded atoms, the reduct is the program obtained as follows. For every rule that contains a negated atom where that atom is in J, remove that rule. The intuition that the rule is false, so you just remove it, that doesn't produce anything. Of the remaining rules, remove all the negated atoms. Because the intuition is the negated atoms will be negations of false, so they will be true. And a dry property here, let me skip this property. Let me show you an example. So here, this was our grounded program. Let's take this J. I'm guessing that WA and WD will be the true atoms. The way to compute the reduct is that you look at the negated atoms. Wherever you see a negation of A or D, like in these ones, you remove the rule. Yeah, so we guessed that WA will be true, and therefore this negation will be false, so this rule will be deactivated, as it were. Of the remaining rules, you would remove the negative atoms. And what we're getting is a Datalog program that is positive, and therefore it has a least fixed point. So we have removed some rules completely. Of the remaining rules, we have removed the negated atoms. What is left is a monotone program. It has a least fixed point. So the least fixed point here is WAWB. You see, we did not guess correctly. We wanted to get J, but we got something else. We'll come back to this. Here is an observation that I need later. If you start with a larger J, then you knock off more rules. We lost the first rule now because WB also makes this rule false. And as a consequence, the least fixed point operator will tell, the least fixed point will be smaller. You increase J, you get a smaller least fixed point. This is a reduct. Giving a set of grounded atoms, we compute a monotone Datalog program through this process that we described. Cool. Stable models. A model J is stable if it is a least fixed point of its reduct. The way to read it is that a stable model is you guess your model, and then you verify that this is a least fixed point of the resulting program that is called the reduct. And if you guess correctly, you call this a stable model. Let's see the stable models for this program, for this database here. Remember, A and B were undefined. We had C was the winning strategy, B was losing, the winning position, B was losing, A and B were undefined. So WA and WC is a stable model. Very bizarre. No surprise about WC. Here, the player one has a moving strategy. But if I declare WA to be winning and WB to be losing, we seem to be doing fine. Player one has a moving, for any node, these rules are satisfied, which means that W is justified by the fact that we can move to B, and B is a losing position. And similarly here, this is justified because we can move to D, and that's a losing position. Similarly, WB and WC, they also form a stable model. Okay, but if we try to include too many, yes.
The greatest stable model is slightly different from the first stable model, right? Because the first stable model, as someone said at some point, like you could argue that this is a okay model at some point. Sorry, the first model.
This one?
Yeah, like at some point, player two can make a mistake and go down, right? But like the other one, like if you go to the second model, this one seems strictly worse in the sense that like this is unrealistic because player one is always going to be in B, so there's really no way player one can get it, right?
I don't know. I'm also wrapping my head around this. I think you could argue that here player one can move here, and that's okay because we declare this to be a losing position, and player two has no choice but to move back. Yes.
I guess I think what you're trying to say is like if you're actually playing this game, you'd prefer to be in the first one because there's no chance of him making a mistake. Like, no matter what moves he makes, he
Okay.
always will win.
So here
Or will
you
he'll be player two. Sorry, if he's player two,
Yeah.
he will never lose.
Yeah, in different player one can never lose an A, and the next one, player B can never win on B. Or sorry, the same graph. Player one can never lose an A, player one can never win on B.
player one right, but we are focusing here on the blue ones, the ones that we declared winners,
Yeah.
and there is no contradiction. You don't really win from A, but you also don't lose.
These are like in chess, like even if the position is draw, sometimes you prefer one drawing position over another because there's no way you can lose from one drawing position, but like
You could do, yeah.
another one, you have to make the perfect move. I think, yeah.
It could be. So a stable model for chess position, I don't know. That's a good question. Folks, I don't know more than this. This is what I know. But they kind of make sense when if you look at them long enough, they make sense. But the important discussion I wanted to have is it's not everything is a stable model. If I guess too much, then what happens? Then I'm going to knock off too many of these rules. I'm only left with one rule. And this rule is not enough to generate as these fixed point, all these three atoms. So the stable model, they have a meaning. You can't guess any model is stable. If you guess too little, then something similar happens. Now you keep too many rules. And as a consequence, the least fixed point now wants to be A and B and C. And we have guessed that only C is a winning strategy. So the only stable models are these two, AC and BC. These are the only stable models. This is a famous stable model semantics. So it was introduced by Gelfond and Lipschitz, 1988. You could argue that it's a principal definition. It makes sure that every fact is justified in any model like Max wanted. It cannot avoid the fact that sometimes we have multiple choices, and this is what the multiple stable models capture. But it has issues. How do we compute it? It is empty hard to check if a stable model exists. So people actually, I should have put this in the slides. There is a pretty well-known implementation, the Vienna DLV, Datalog Vienna, something like this. Maybe Max knows about this, which supports stable model semantics. It uses a technique called answer set programming. And is used for constraint satisfaction. It's not so much for computing queries over data, but it is for constraint satisfaction. So getting back to stratified Datalog, a stratified Datalog has a single stable model. Yes.
Do you happen to know if answer set programming, the relationship between stable model and Datalog and answer set programming?
My understanding is that answer set programming computes the stable models or one stable model, but I may be wrong. I really don't know. Right. So I wanted to go back to Max's question. How principled is it to take a stratified Datalog program, here is a stratified one, and consider its perfect model, which we compute stratum by stratum? And the answer is it's very justified because the perfect model is the only it is the only stable model. So I just have this little example here. I'm not sure how good it is. So A of 1 is true because there is nothing on the body. Then the second stratum is B, which is the negation of A of 1. And the third stratum is C, which uses a negation of B of 1. According to stratified data log, we need to proceed stratum by stratum. First, A of 1 is true. Then we compute B, which is false. And then we compute C, which again becomes true. And this is indeed the only stable model. Because if we knock off this rule, the B, and also this rule, then we get the reduct only computes A of 1 and C of 1, which is exactly our model. But beyond that, there is no other stable model. Okay, any questions about stable model semantics? There are easily dozens, if not hundreds of papers written on the stable model semantics and all its implications. Yes?
So in this minute, the one you put, I mean, like, we put negations in the head, we have disjunctions in the head. Like, I think all of those things should be.
So I'm pretty sure that the answer set techniques allows that.
I believe they do.
Yeah, and I think stable model semantics extends to those constructions.
Are there non-stratified programs, unique stable models?
Yeah, for example, this one. This is not stratified.
There are like two, right? There are two of them.
There are two stable models.
Yeah, I was asking if there are non-stratified programs with unique stable.
With unique stable model. Well, if your graph happens to be acyclic, then you have a unique stable model, indeed, just the winning strategy, the winning positions. So it also depends on the data.
Wait, would acyclic, doesn't that imply that it would be
Let me see if I can get here.
Acyclic implies that you could construct the stratified data log program, and the stratified data log program has the unique stable model.
yeah, that was what I was asking. Is there a non-stratified model that has a unique
Stable model.
stable model?
Yeah, I don't know, but you have a good point. So this is a non-stratified program, but if you ground it on any acyclic graph, it becomes stratified. Just because you know this grounded atom will be in a higher stratum than this atom here. So when we talk about the stratified program, we need to be careful if this is the original program or it is the grounded program. Okay, good, cool. Let me show you the other semantics, which is actually more fun, the well-founded semantics. What is it? Here is a well-founded model. And this goes as follows. The well-founded model, it has a complicated justification, which I never understood, but the operational semantics is very intuitive. You use your current state of the IDBs to compute the reduct. And then once you have the reduct, you compute its least fixed point because this is a positive data log program, a grounded one. Compute its fixed point, and then you use this to compute the next reduct and compute the fixed point. Okay, I don't think I did a great job to explaining this, but let me do it like this. We start from the empty set. I should say here J0 is, yeah, I said this. J0 is the empty set. When we compute the reduct is as big as it gets. So none of these rules gets knocked out. So we just remove the negative atoms and we keep all the rules. So my question is, what is J1? is the least fixed point of the reduct. J1 will contain WA, WB, and WC. Yeah, because yeah, all of them will be in. So this is J0. Initially, everything is false. And when we compute its reduct, we get all these rules in blue. And therefore, J1 contains all these facts, all these ground atoms. J1 is as big as it gets. Now, when we compute J2, we compute the reduct based on J1. So this reduct is going to knock out the first three rules because of the ABC here. So this is we are left with a pretty small program, but it's slightly bigger than J0. So J2 is bigger than. This is how we get these ascending chains of the odd of the even steps, and we get a descending chains of the odd steps. And now when we compute the reduct of J2, we get again the same three rules, and now we have reached the fixed point. Yeah, because the next one will be the same. You seem to like it.
It feels like gradient descent with like your step size is too big. So you're just
The thing because gradient descent has kind of hundreds of extensions. Is there such an extension? They go too far and come back. But yeah, it fits like this. So then what happens is that you take this chain of the even IDBs, the even IDB steps, and you take their union. These are the certain facts. And in our case, the certain facts are just W of C. And on the other side, you take the intersection of all the odd or odd number IDBs, and these are called the possible facts.
Wait, shouldn't it be the other way around? Shouldn't we, like, we want to be certain about a fact, shouldn't we be intersecting it?
Yeah, it's a good point. This is correct, but you're right. In general, if we have an incomplete database, the intersection are the certain facts.
You're adding certain.
also you have like inclusion. So I feel like maybe a clear way to say this is like the largest even one is a certain fact, which is equivalent to the union of all of them.
Yeah. But Max has a point. So can we explain the certain facts as the intersection of possible words? And it turns out you can, these are the intersection of the stable models, but unfortunately with the stable models under free valued semantics. And I didn't want to go there because I don't fully understand that either. Okay, now this is, to me, this is very appealing. This is something you can compute in polynomial time. And I think it's much more informative than, enumerating all those stable models. I don't know what to do with them. But here, if you tell me this is unknown, I find this very informative. Plus, you can compute this in polynomial time.
You could, I mean, this is the syntactic transformation of Datalog, more or less, right?
Why is it syntactic?
Well, I mean, like, you could implement this by not modifying a Datalog engine and just invoking it.
Yep. Yeah, maybe you want to, yeah, I shouldn't speculate, but you see the potential here. Okay, so well-founded models can be computed in polynomial time. And I don't know why systems don't support it. I'm not aware of any system, I'm not aware of many systems, period. But the few that I'm aware of, they do not support stable well-founded semantics. My guess is, maybe your guess is better, my guess is that they don't like to talk about this free valued logic. How can they return the answer? If they return the certain tuples or the possible tuples, how do you make this compositional? You want to take the answer and feed it into another program, and now you have free valued logic. Yep, so that is a story about well-founded semantics. Yes, Grace, you had a question? No. Okay, so the other two extensions I want to describe, they are motivated not so much from the logic perspective, but from a computational perspective. This is what you would implement. If you already have a Datalog implementation, then this is how you can deal with negation. You could compute what's called an inflationary fixed point, or you can compute what's called a partial fixed point. The partial fixed point is more theoretical, but the inflationary fixed point kind of makes sense. And I'll show you what it means. Here is what the inflationary fixed point means. You compute the sequence that we know and love, where at the time t plus 1, I forgot to put it in the superscript. At time t plus 1, you apply the immediate consequence operator. But since the immediate consequence operator is no longer monotone, you union with the previous state of the IDBs. Let me remind you that in the first lecture, when we discussed Datalog, I think it was on the whiteboard, this is what some of you wanted to do this, just union with the previous state. It's so natural. We don't need to do this if TP is monotone. But if it is not monotone, then if you union this, then you guarantee that the sequence of states is increasing. Since it's increasing, it can't increase forever. It needs to finish after a polynomial number of steps. So this is a little theorem that the inflationary fixed point of a Datalog program can be computed in time polynomial in the size of the input database. I asked why, but yeah, the answer is straightforward, because this increasing sequence can only add polynomially many tuples before it runs out of tuples to add. So this is something to take away. Inflationary Datalog is always in polynomial time, like Datalog was, but now we also support negation, then we are still guaranteed to express only things that are in polynomial time. The other one is a partial fixed point, which I would call it even more brain dead. Here, without any apologies, you simply compute the sequence. You just apply the immediate consequence operator and get JT plus 1. It might grow, it might shrink, it might go sideways. We don't know. But if you ever reach a fixed point, if step t0 is the same as step t0 plus 1, then you stop. Victory, this is what you return. And if not, do you run forever? You could run forever, but you can also detect termination by having a counter. Because you know the space used by these IDBs. The space is polynomial in the active domain, like n to the power k. So you only need a counter that counts up n to the k. And if you reach that counter without a fixed point, then you know you're going to loop forever. And this is why this theory paper, they say in that case, you return the empty set. Brain dead. What you can prove is that the partial fixed point is computable in polynomial space. We don't need more than polynomial space to store these IDBs. But how long does it take? Well, that can take forever. It can take an exponential amount of time. So these are the two extensions: inflationary fixed point and partial fixed point. They're especially interesting because, as I will show you in a couple of slides, they capture these complexity classes, polynomial time and polynomial space. And Connor, he's a big fan of these descriptive complexity, so he's not here, but he will enjoy this slide.
Can we think of this, I'm just wildly brainstorming here, as sort of operating over another space representing the set of all things that we've seen so far? I don't know if that gives us anything useful.
Right, so if you want to record all of them, there are exponentially many. You need to represent the time somehow, and the time can be exponentially big. So then you need the exponential amount of space.
That's why you just use count.
Yeah, so you can use a counter just to detect that you're running forever, but you can't look at the history. The history is lost if you want to stay in polynomial space. It's totally unpractical, so nobody has implemented this, nobody considers. But the inflationary fixed point is more appealing. That is in polynomial time. And before you implement this, look at this slide. Here is a simple exercise. We want to compute the complement of the transitive closure. Yeah, kind of the simplest data log with negation. So how do we compute it? Well, in stratified data log, we would compute the transitive closure. And in the next stratum, we compute this complement and we declare victory. What happens if we compute this program using inflationary fixed point semantics? So notice that the state of the IDB consists both of the transitive closure and the answer. Okay, so as you think about those intermediate steps where they grow, what happens to the transitive closure? That doesn't depend on the answer. So what do we get here when we do the inflationary fixed point?
The regular transitive closure.
We get a regular transitive closure. Union with the previous state doesn't change anything because the operator was already monotone, and we get this increasing sequence. But
Actually,
what's the answer? What is the answer after the first step?
it's the Cartesian product, right?
It's a Cartesian product because T was empty, so not T is true, and answer is a Cartesian product, and it will never go back. It's inflationary. So once it's a Cartesian product, this is what it stays. Big question. Can we compute the complement of the transitive closure in inflationary data log? It's surprising. I didn't know this, but it goes back to, it's a list of pretty famous results. Here is how you do it in an extremely concrete way. You define a program that under inflationary semantics keeps track of when the transitive closure has finished. And you do this by computing a second IDB predicate. I called it T previous, which is always one step behind the transitive closure. You can find this written in various ways, but this is sufficient. So you compute the transitive closure, and T previous is just the transitive closure. It's always one step behind. So now we need a little bit of acrobatics to use this one step behind to detect when they become equal. At some point, they will become equal, and this is the signal that we can stop. So C is a signal that we want to continue. C says there exist two nodes in the transitive closure which are not yet in the previous transitive closure. Oh boy, I hope this is good. I'm not sure it's good. So it means this is typically true. So therefore, this is false. No, this is wrong. I screwed it up. I tried to make it up myself, and obviously I didn't get it right. And it's not easy to get it right. I don't think I can fix it here. You see the problem. Once C is true, it never becomes false. I wanted it to become false when there is no such U. Here is how we can fix it. Once it's true, it's true. So it's over. So somehow in the answer here, I want to trigger this only when we know that we reach the end. So this needs to be fixed. As you see, it's totally unclear how to do it, but it's possible. So this was the history is long, and I'm also confused by the history. This particular example was found by Immermann, but it builds on a much older observation from the least fixed point semantics of personal logic, that you can But you compute what's called a stage comparison relation. You can take two tuples and you can check if one tuple is going to be computed before the other tuple in the least fixed point. This is not quite like this because this refers to an inflationary program, and this is credited to Unerman. So it turns out that because of the correct way to express a complement of the transitive closure, which I got wrong here, everything you can express in the least fixed in LFP in least fixed point logic, you can also express in Datalog with inflationary semantics, with inflationary fixed point semantics. You get negation for free. And vice versa, everything when expressed in Datalog with inflationary fixed point semantics, you can rephrase using monotone operators in first order logic, maybe without universal quantifiers. So this part is blurry, and I apologize for screwing up, but this is a challenge for you. Look up the correct implementation of transitive closure. It's in the book Abiteboul, Hull-Indiano. It took me a long time to understand, but I don't have the book with me, so I thought I can reproduce it. Good, cool. So the last slide I want to show you is that famous slide that Connors wanted to see, descriptive complexity. And it begs the question, what is the connection between the problems that we can solve in, say, inflationary Datalog and the problems that are solvable in polynomial time? Everything solvable in inflationary fixed Datalog is also in polynomial time. Is the converse true? The converse is false for a trivial reason. Parity, the parity of a relation of a unary set, we cannot write it in Datalog. We cannot write it in inflationary Datalog and partial Datalog for partial fixed point. In any variant of Datalog you can imagine, you cannot write parity unless you add explicitly an operator that looks at parity. However, if your database comes with an order relation, then you can use this order relation to compute parity and a lot more. Now, once you have the order relation, you can also compute the successor. You can check if X is strictly before Y in your active domain. And you can also compute the minimum X and the maximum X. It's a simple exercise. How do we compute parity if we have an order relation? So think about a single relation R. It has many elements. Yes?
Parity of the smallest thing is even, and the parity of the successor, the smallest thing is odd.
Yeah, that is the idea. So it's going to go odd, even, odd, even. So what if you sort the elements in the relation R, if you sort them by the linear order, how long should this path be from the smallest to the biggest one? What kind of length do you need to see? An even length. Yeah, we want the path from the minimum to the maximum to be even. This is what we know how to compute. We know how to compute the pairs of nodes X, Y that are connected by an even length path. So we start with successor followed by successor. And then you can add one at a time, but I prefer to do the doubling just because it's shorter. So if X, G are connected by an even path and G, Y by an even path, and so are X, Y. And I don't need to care about odd lengths. And then the relation R is even if it contains an element X and another element Y. X is the smallest element in our order. Y is the smallest element in the order, and there is an even length path from X to Y.
Why do you want the path from the smallest to the largest to be even?
Oh, because it needs to be odd. You're right. It should be odd.
Why does it have to be odd?
Well, if the relation has two elements and they are ordered, then I have one edge from the first to the second.
Yes.
If it has four elements, right, then I have, let me go it from here, 1, 2, 3, 4. The number of edges is 3.
But what if I have 5 elements?
Then the number of edges, if I have 5 elements, then it is odd. And I wanted to check if the relation is even.
I see it.
Okay, so finally, this brings me to the celebrated complexity results. Mostly Vardy, but also Immerman later, they prove the following. If you consider Datalog with negation and inflationary fixed point semantics over ordered structures, then it can express precisely the queries that are in the complexity class polynomial time. And if you replace inflationary with partial fixed point semantics, then you can express precisely the problems that are in polynomial space. This is a way to capture complexity classes using logic. Although the critique is that once you add order, it's not so much logic, it becomes more like programming. Okay, I really wanted to show you the descriptive complexity. It's a classic result. Connor is very fond of this. Neil Immerman, he's at UMass, and Connor was there, so he talked to Neil Immerman. So that is my last slide. Datalog remains a simple and elegant and super appealing formalist, and many people embrace it today. There is a new resurgence of interest in Datalog. How do we deal with negation and with aggregates and with anything non-monotone? Just stratify it. The stratified Datalog is good enough for most practical purposes. Beyond that, it gets more iffy. There are many alternative semantics, and especially these ad hoc extensions that are based on computation, inflationary and partial. I think they are debatable at how practical they are. But they are very interesting from a theoretical point of view. And here is another celebrated result by Abitaboul and Diano. Actually, this paper also added Papadimitriou. So this is Abitaboul, Papadimitriou, and Diano. They proved the following, that if you can show that showing that inflationary fixed point can express the same problems as partial fixed point, then you have proven that P time is equal to P space. And conversely, if you can prove that these are not equal, then you have proven that P time is different from P space. Yes?
Isn't this implied by the theorems on the last slide?
One direction is implied.
Okay.
Let's see which direction. The direction from left to right. If these are equal, that means equal over any vocabulary.
Mm-hmm.
In particular, they would be equal even if I add an order relation. And that means that P time is equal to P space.
Oh, okay. Actually, before it was with the order relation.
Yes. Now, if I don't have order, so let's put it this way, if P time is equal to P space, but I don't have the order, then it's not immediately obvious how I prove that every partial fixed point can be expressed with inflationary, but it turns out you can. Cool. That was a lot of classical theory on Datalog. Let's stop here. Next week we have one more lecture, and I was planning to show you anything fun. And for me, fun means probabilistic databases. That's what I plan to show you. Yeah. So come to hear about probabilistic databases, and then we have the presentations, and that will be it. Okay, good folks. Good luck with preparing your presentation, and have a happy Thanksgiving.